Could heat capacity vary when we have a solid or a liquid? Well, remember the basic difference between the two heat capacities when we were dealing with a gas is that one has significant change in volume. It has to push the atmosphere out of the way significantly. Whereas if we have a liquid or a solid, it just doesn't change volume very much at all. And so for solids and liquids, the heat capacity doesn't matter if you take it at constant pressure or constant volume. You get approximately and very close to the same number. In other words, if I built a super reinforced structure and I made it so that the volume of, let's say, some liquid water was forced to remain constant, and yet I changed the temperature of that water and measured how much energy it took to change the temperature of the water, I would get about the same amount of energy as if I had just let the water be open to the atmosphere and add thermal energy to it. And the reason is because, yes, there's a small change in the volume of the liquid, but it's not much. It's not near as much as the volume change that gases experience, for example. Solids work the same way. And so normally the heat capacities for solids and liquids are reported as a CP value because that's how they're measured. There's no point in constraining the volume of the solid or liquid, which is extremely difficult to do, when you can simply measure the heat capacity at constant pressure, and you get essentially what you would have at constant volume. So if we think about the heat capacity of solids, we can approximate the change in internal energy as some average heat capacity times the change in temperature. Now if we think about enthalpy again, enthalpy is U plus PV. We can write the differential form of it as dH equals du plus VdP, and here we're using that calculus rule where we have to hold one variable constant multiplied by the differential of the second and then vice versa. Well, for the case of solids, the dV term is going to be approximately zero. It's going to be very small. And so all we're really left with for differential enthalpy changes are du plus VdP. And so delta H's macroscopic changes in enthalpy of systems would be equal to the change in internal energy plus the specific volume, which is pretty much constant, times the change in pressure. Now, many times the change in pressure is small and that second term is so small we can just neglect it. Now, this is not completely true, but to a good approximation this is true, especially for solids. Delta H for a solid is close enough to delta U, which is an average heat capacity times the change in temperature. So if you wanted to compute the enthalpy change of your car's block, or you wanted to compute the internal energy change, they'd be, for all practical purposes, the same thing. Now, if we want to take that a little bit farther, we can consider that change in pressure. As a matter of fact, we can use this equation, if we include the delta P, as an approximation for liquids. So for a liquid, we can improve our estimate of enthalpies at some pressure and temperature based on the enthalpy of saturated liquid. Now, you may not remember this, but what we normally did was we said, well, if we need the enthalpy of liquid in the subcooled liquid region, we can just approximate it as the enthalpy at saturation at whatever temperature we want it at, right? And that'll be close enough. Well, this allows us to improve on that, at least sometimes. It doesn't always improve, but it, in theory, should get us closer, because if we include that V delta P term, we should be able to calculate the difference in enthalpy between our actual subcooled liquid state and the saturated liquid state. And that's what this equation is doing here, where we have enthalpy at a given pressure and temperature can be approximated as the enthalpy of that liquid at saturation at the temperature plus the specific volume of the liquid at the given temperature at saturation, of course, times the difference between the actual pressure that the liquid is at and the saturation pressure. Now, obviously, with this equation, if there's very little change in pressure over whatever process the liquid is undergoing, then the enthalpy change will be approximately C delta T. On the other hand, if there's practically no change in temperature but a change in pressure, then the enthalpy change will be V delta P.